this. All right. So we're going to focus in on from how to what. So let's talk about that. Take a look at this mystery operation, and let's dissect it. Let's take a look at what it does. And if we analyze the code, it tells us how. So it takes an array of numbers. It creates an iterator, a sum variable, and a new array. Line 2. I'm going to call out. I think I'm going to. Well, no, that's not going to work either. What else? It iterates through that original array. So I'm about here now, right? It pushes to that new array the value of the current index multiplied by itself, and then it loops on that new array, and it adds the value of each one to the sum, and then it returns the sum. So that's the how. So somebody tell me what it's doing at a higher level.
Sum of squares.
Sum of squares. Yeah, thank you. So let's change the conversation from how to what. Same block of code, exactly, or it should be. If not, then I made a mistake. But this block of code at the bottom is more of the what. But it produces the same output. It runs the same logic. So abstractly, it maps from. So now I'm going to do the same thing with this code. You start with an array, numbers. It maps on that array and squares it, and then it reduces. We get the terminology up on the screen. Oops. It reduces that array of squares to the sum. So this is one of the goals of declarative style programming, of which functional is like a sub-paradigm of declarative. Is to take a look at our code where what is the same as how. Now, so let's look at another one. Okay, you tell me from a what perspective, what is this doing? So that more abstract. Louder? Somebody had it, maybe. Okay, it's kind of hard, right? You're still, this is not yet from our new perspective.
It's a sum of even numbers divided by 2.
Okay. So, yeah, easy, right? Okay. It's kind of hard to get to that point. He had to roll through all that code and keep track of it all in his head to get to that point. So if we rewrite it to the what, we have let me back up. We have an array of numbers. We filter down to the evens. We map their halves, and then we reduce to an average. And that's where, of course, is even, half, and to average are just pure functions. So let's look at the pseudocode of that. Take an array of numbers, filter out the odds, map to halves. The pseudocode looks a lot like the functional code. Not only is it shorter, well, kind of if they're named properly and you can focus here instead of here or here. Not only is it shorter, but it's easier to reason about, easier to read. So, and I think that this leads to some of the benefits that we described earlier, especially kind of the fun part, the easier to reason about part. So let's take a look at if this idea of going from how to what can scale. So first, let's talk about what an app does, and if we can apply that theory, going from how to what to see if that works. So in an app, you have things, and things have names, and things have functionality, and they have data, and they have ways to interact with the other things. and they have a tendency to be really domain specific. But that's still the how. What's the what for an app? You know, from an abstract level. True or false, an app is just a long-running process in which an async series of events transforms into effects. Anybody? True or false? I say true. All right, so we have a start. We usually start with an event and some state. And that data and that event flows through some transformations like so. And then we end up with a state, a mutation, or an effect of some sort. Kind of like that, a little visualization. So basically an app listens for events, pipes them through these transformations, and ends them as effects. Is that what an app does? I think yes. Are you buying it? All right, do you think I'm crazy? Cuckoo? No? Okay. All right, so some examples. Your app started. Examples of your starting point. Okay, so your app started, maybe a DOM event occurred, like a click or something. You received an HTTP request or you sent a response. These are the starting points of that flow, right? Think of the flow. Maybe you got a database result or a WebSocket message. If state is really just data and events are really kind of just data, then we can really think about everything more simply. It's all just data, right? So let's look at some end examples. Some of the end examples overlap the start examples, right? We updated the UI or we triggered a different DOM event, created a request or a response, saved the database, etc. So we have a start and we have an end and we have a bunch of stuff in the middle. And so let's talk about the stuff in the middle. That's kind of the important stuff, right? Instead of things with imperative operations like these, set attribute, add grade, etc., the declarative or functional style programming strives to align how with what. So quick story, we were interviewing a person for a front-end position, and he was telling us about how he dealt with incoming data in the browser. And he said that he got his array of data and he looped through the objects in the data and he newed up JavaScript objects so that he could work with them in the browser. And it illustrated that he didn't have a fundamental understanding of the environment that he was in. He had brought forth his object-oriented perspective of his programming world and he applied it to the browser. And we want to shift our thinking from, when we're in the browser at least, and possibly other areas where it makes sense, not everywhere necessarily, but where it does make sense, we want to shift our thinking from objects with relationships and functionality to a flow of data through some transformations. So, and yeah, so transformative verbs. These verbs can describe what those transformations are doing. So like filter, slice, map, reduce, concat, zip, fork, flatten. They're all core to functional programming. So true, it's not always that simple. Maybe it looks like that or that or that or that. And sometimes the end of one flow is actually just the beginning of the next, like that. Nevertheless, all the transformations in the middle can be represented with those verbs. And if, as a bonus, if we follow some rules and best practices, then these transformations can become extremely reusable and easy to maintain, etc. Easy to reason about. So we promised to talk about arrays, so let's do that instead of all this preaching. So typically the data, when it comes into our app, we get it in the form of an array, and we deal with that data in bulk with other data also in the form of arrays. And this array data eventually makes changes to the DOM, at least in the browser world, or the equivalent to whatever world you're in. So the array is kind of this, like a candy store for functional programming. It has some of those verbs, specifically those right there. And we're going to talk about most of those. And so these verbs are not just methods off the prototype of an array, they're part of this bigger paradigm of functional programming. And because of that, we can tap into their power that comes from composing those verbs together as we flow through our process. So you don't have to adopt the whole thing all at once. You can use it where it makes sense, obviously, all the time, but start using it as a little bit at a time as it fits into your style or timeline, etc. So, but first, before you can start using it, you got to understand the parts, and your first stop should probably always be MDN. It's pretty good documentation there. So slice, the first verbs that we'll cover, slice. It returns a shallow copy of a portion of an array into a new array. And it's a declarative way of grabbing a piece, slice or a piece of an array. So basically you start with an array of a certain length and you end up with a new array that's smaller, usually.
When you say shallow, you mean it still has reference to the original array?
Shallow meaning that, so it's going to take a copy of an array, so you're applying some immutability there. We're not going to modify the original array. If that array has object references in it, it's going to copy those one layer deep. So if you're deeper than that, you're going to still have the same references. Does that make sense? Is that what you're asking? Yeah. Okay. Let's see. In the signature, you give it two parameters, the starting point and optionally a length. So here's a quick example. If you have an array with 1, 2, 3 in the letter A, and then you call .slice on it, and you give it 0 as the starting point, so start in the first position, and it will, in second parameter, you give it a 3, so tell it to go for a length of 3. You'll end up with an array of 1, 2, 3. So basically, you sliced out the 1, 2, 3, and you left off the A on the end. All right, so concat, our next verb.
Bruce?
Yeah.
How is the second part optional? The second parameter?
It'll go to the end. So if you were to tell, if you had one of length 10 and you told it to start at position 5, it would go from 5 to the end.
Oh, I see. Okay.
That's a good question, thanks. So concat combines items into a new array. So the rules are you start with an array and you end up with a larger array. And it creates a new array from the items in the original array plus the items in the argument. And if the argument coming in is also an array, it will shallow flatten that. So let's take a look at an example to illustrate how that works. So on the first one, yeah?
Sorry, I'm just going to expose my ignorance and don't care. Do we start at 0 and we start at 1?
So you want?
You know, in JavaScript,
It's 0, yeah.
It's always 0 based.
Yeah. Are there any exceptions to that? Does anybody know? I don't know of any. No? Okay. All right, so in the first example, we have an array 1 through 10, and we concat 11, and so we just end up with an array that has 1 through 11. Simple. On the second one, we have that same array, 1 through 10, in it, and notice that we're concating, in our call to concat is actually an array. So here we're just passing in 11. Here we're passing in an array that contains 11, 12, 13, and what? Object. Yeah. So when we call that concat, well, should we look at it? Because I don't know that I can. So notice we don't have 1 through 10 and then an array. We have 11, 12, 13, and object. So that's how that works. Any questions about that one? More questions? All right.
So how would you concat an array of arrays?
And flatten it or just keep it
You would just dump an
And so it would flatten it one layer deep. So actually, let me hang on to that a second. One of my examples does just that, I think. So we'll get there. And if it doesn't, bring it up again. We'll cover it. But I think it does. All right. So now on to the map verb. This is the one I use the most for sure. Map transforms each item. That's the simplest way I can put that. The size of the array can't change, has to remain exactly the same. And it does produce, like the others, it does produce a new array when it's done. So it's a higher order function, so refresher or new information if you haven't had it before. A higher order function is a function that accepts or returns another function. And then map accepts a lambda function, so that's what made it a higher order function. And refresher on that, a lambda function is, does anybody want to answer that one for me?
Placeholder of each item as language loops through the array.
Okay, that from that perspective. So more generically though, did you want to stab at it?
Inline function that's not given a name.
Right. So in our code right here, we're assume that we had some contents in this array here, and we were calling .map on it. The argument we're passing is this. That's a lambda function. It's also using ES6 arrow syntax, so if you don't know that yet, learn it. It's awesome. Okay. Let's see where I'm at here. Okay, so did I explain that right? Yes. Okay. So first argument is that lambda function, and basically map is looping through your array, calling that lambda function for each element in that array. And the return value of your function is what gets placed into the new array. Okay, so some examples. For the first one, we got an array 0 through 7, and we call .map on it. And we pass it, let me highlight code here. I think that's working okay. We're going to pass map this lambda function, oops, not working, this lambda function right here, which basically multiplies the current element by 2. So when map loops, it passes the current element of this array in this position right here. And then we just multiply it by 2. So we end up with a new array where all the items from the first array are multiplied by 2. Okay, next example, we have an array of objects with W, H, and D. So kind of think of those as 3 dimensions: width, height, and depth. And we're calling map on it. And the lambda function we pass it is here. And then notice the curly brace syntax. So map's going to call that lambda function on each of those objects in that array. The curly brace syntax here is destructuring of that object so that we can just reference the properties of it, those properties of it directly. And then we're basically calculating the volume.
So you could have done an X and an X dot W, X dot H, X dot D.
Yep, I could have, exactly.
Now, does that change the original array, or does that still, yeah, it changes the actual array that you had, right?
It does not touch the original array. So what it returns is a brand new array. So remember the rules of map where the size of the array doesn't change. So this array, so the array we end up with will be exactly 4 items by definition. This array will not be touched. And the new array coming out will be a brand new array. Here, yeah, let's look at that. Looks like we've got a JS bin on that. Let's do it. Should we modify that? Oops. And did I forget anything? Oh, what's that?
Just
Comma A? What?
So we can see that it didn't change.
Oh, comma A, thank you. That's a great way to do that. Right there, right, wait, where's my, right there, thank you. I'm a little slow, but I'll get there. So there's our, let's clear that, try again. So here is our, let's go from the bottom up. So here's our old array right here, right? Where am I going? Right to there. There's our old array, and there's our new array with the volumes in it. Okay, any questions about that? So next verb, filter. So filter does basically what it says. It removes items from an array. So you start with an array of a certain length, and you end up with one that's, you end up with a new array that's either the same size if nothing gets filtered out, or possibly smaller, typically smaller. It has the same syntax pattern as map. You give it a function for it to call on each element in the source array. And it builds a new array using each item of the original array for which the function you pass it returns true. Is that too many words to? Okay, let's do the example, or the more of the definition. Maybe we'll clear up. But stop me if you're not getting it. Stop me, because filter's a good one. So you pass it. So filter's a higher order function, accepts a lambda function just like map. The first argument that you pass it is a placeholder of, okay, the first argument in your lambda function, so that guy, is a placeholder of each item that it's looping on. And then the return value determines, so this is saying, hey, if it's even, return true. So as long as it's even, it will stay, will be included in the new array. So some examples, there's our even one right there, 1 through 10, and we'll end up with a new array with all the evens that were in it. And then the next one, who wants to tell me what that one's doing while I pull up JSBin?
Check and see if there's bacon in the string.
Okay, and then if there is bacon, is it included or excluded? Yeah, I think you're right. Okay, so the first one were the evens. That's the top of their piece. And then the second one, everything that had bacon gets included. Everything else gets filtered out. So if you're not familiar with that syntax, that's just regular expression in JavaScript, case insensitive, then run the test on that value that was coming in on our lambda function. Okay, any questions on filter before I go to reduce? It's only going to get, it's not going to get any simpler from here. So, all right. Oh, I don't have focus. Hang on. All right. So, reduce loops on the elements of an array and reduces it to a single thing. So, question?
Yeah, I do have a question. So, just trying to get my head around this. Based on, sorry, I'm about 7 sentences behind you.
No problem.
The process was not as fast.
There's probably 3 more people with the same question, so you're
Yeah.
good.
So, I don't mind embarrassing myself. So, given what you just said about filter, where the lambda function you provide to the filter operation performs its operation on everything where the condition evaluates to true, is it a correct statement then that the fundamental difference between map and filter is that map operates on every value, the filter only operates, performs its function, the lambda function, on those values where your condition is true? Or am I missing something?
I think you're close. Maybe the way you're thinking about it's correct. Let me word it a little differently and see if this still resonates with you. map and filter are going to essentially both loop on the source array. So if you have a 10 item array, there's going to be 10 iterations going on in the background. Where they differ is that on map, whatever value you return from the function becomes the value in the new array. But filter, you just give it a true or false to tell it whether or not to include the original value, their value from the original array or not.
So that was close.
So map is do something to every item and element in this array and make a new array out of that something. And filter is get rid of some of these things. I don't want them all. Okay, you're welcome. Stop me anytime. Any question? So where were we? Okay, reduce. So reduce loops on the elements of an array to produce a single thing. So you go from an array of any number of things down to one thing. Could be anything, but it's one thing, and that's the definition, the rule. So the example here calculates a sum, and that syntax deserves some explanation, but let's visualize it a little bit first. So let's say that you have an array of blue circles and you want to end up with a red square. And I realize that you typically work with red circles and blue squares, so just bear with me there. It's just a visualization. So yeah, okay, so let's talk about that syntax a little bit, and then we'll visualize it again. So you give it a lambda function. It's higher order function, just like the last two. Of your lambda, so here's our lambda function, right here to here. So the first argument is the accumulation of values. So this is that object or thing that you're building up, that one thing that you're building up as you loop through the original array. So that gets passed to the next iteration through this argument here. Then the second one is the current item as it's looping through that original array. And then the return value of your function, whatever that returns, becomes the accumulator in the next iteration, like we said. And then the second argument of your call to reduce is an initial value. So in our case here, we're doing a sum. It makes sense to start with 0. So you just have to put in there whatever makes sense for what you're trying to do. So you could start with an empty object. If you leave it off, it's going to skip the first iteration, use the first item in your source array as the starting value of the accumulator. But I like to be explicit about my calls to reduce. It helps me reason about it, so I would just always put a starting value. I don't think there's any situation where you couldn't put a starting value. Haven't thought of one yet, anyway. So let's visualize that again. Array of blue circles. We're going to seed the initial accumulator value with the red square. And then reduce is going to take that red square as the first argument to your lambda function and the first item in the array as the second parameter to your lambda function. It's going to run your lambda function, and your lambda function is going to return something. That now becomes your red square, and this pattern repeats. So your return value then becomes the first argument, and the next item in the array becomes the second argument. Over and over again, just like that, until you end up with your last red square. So with the numbers in place, we seeded it with 0, right? See in the code, our 0 right there became our 0 here. And so 0 and 1 became the two arguments to our lambda function. So 0 and 1, right? Okay. Be quiet, Jared. And then our function added them together and returned 1. So now 1 became the first argument, and 3 became the second argument. Added them together. Now 4 becomes the first argument, and 2 becomes the second. This is kind of complex. I realize it's complex. So I think you gotta try it. You gotta use it. if you find yourself looping in a functional paradigm, you're probably doing it wrong. So you need to figure out which one of those verbs fit your situation and use it. And just look it up on MDN and just use it. So then the pattern just continues until you're done summing. Okay, so what else can it do? It's going to answer your question, I think, I hope. You can shallow flatten arrays. So the result of this would be a single array flattened. Any questions about that? Okay. You can split arrays. So in this code, you pass in a chunk size and it'll split it up. Kind of like that. Not kind of, but actually. You can compose functions. This function accepts n number of functions as an argument, and it returns a function that when you call it, will run in the argument, run an argument through all of those functions. And it uses a reduce write instead of reduce. If it was using reduce, it would be a pipe instead of a compose, I think. You can curry functions. Curry is the technique of taking a function that accepts multiple arguments and translating it into a function or functions that accept less or one argument. So one way to think about that is, let's say you want to make a database connection. I'm a database guy, so that resonates with me. And you had, when the app starts up, you know what database it is, so you know the URL, but you don't know the username and password. Maybe you're connecting differently depending on who's logged in. Or something of the sort. So you might curry that function that would have taken a URL and a username and password, curry it so that you just pass it the URL, and you wait till later to call it again, or the curried result, with the username and password, or maybe you curry it three times. You curry it 3 times so that you just call it once with the URL, then you call the result of that with the username, and then you call the result of that with the password. So that's an example of how that works. You can create a promise thunk waterfall. Probably don't need to explain that. Everybody's got that, right? So this is useful when you have an array of functions that are promise based, and you want them to run serially instead of all at once. It's interesting. Look how little code is there to do kind of a complex thing, right? You're forcing asynchronous things to run synchronously, and you're doing it in like 4 lines of code. That's kind of nuts, if you ask me. All right. We got about 8 minutes left. Let's skip the demos. The demos are basically what I just showed you in the slides. Let's instead do an exercise. Does that sound all right? Or does somebody want to see? Okay. All right, let's do an exercise. So here's our exercise. Let's say we're consuming an API, and it gives us data that looks like that top code block, which is kind of gross if you ask me. But you don't always have access over, you don't have control over your service endpoints. Maybe somebody else does. We want to consume it and have it in our app looking like that. And not only do we want to take out the gross key value stuff going on there, but we also wanted to leave off the price because the Minister of Finance will never let me buy a Porsche if she sees the price tag first. So let's get that out of there. Any guesses on what verbs we're going to need here to make that happen? Filter. What's filter going to do for us? Okay, what else are we going to need? Why are we going to need map?
So we can transfer each value.
Okay. Anything else? Somebody said reduce? Yeah. Okay, let's try it. Let's code it. This is where you all pray that, oh, actually, I cheated. I got one that's, where is it? There. I shrunk up, this is the same thing. I just shrunk up the objects here so that I wasn't coding down at the bottom of the screen, so you could all see it. This is where y'all cross your fingers and pray for me that the demo goes well. Okay, so let's run this so you get a starting point. I can barely see what's on that screen. So if I do something wrong, you tell me what I did wrong. Run the angle I'm at goes crazy.
Do a console instead of output.
Oh, thank you. That is it. Console. All right, and then that's good enough, I think. All right, so basically our starting value, we've ended up with what we started with. There's no change. Thank you. Ah, that's it. Thank you. All right, so let's get rid of that semicolon because I like to give people heart attacks. And it's going to just be in my way while I code this. So let's get rid of the price first. What did we say we were going to use for that? Yeah. Okay. So anybody want to feed me the code? Well, here's the signature of filter. We're going to give it a lambda function like that. Oops. Did I do it right? Almost. So there's a skeleton of our lambda function. What comes in right here? Anybody remember? Okay, and I'm going to destructure that and just pull out the key. So for filtering, all I need to know what is the key. I don't need the price at this point. Then, how should I filter that out? Okay, I'm gonna do an implied return in ES. Okay. Key not equal to MSRP. Anything else? Did I get it? Did it work? Okay, price is gone. Yay! Okay, now I have a chance at my Porsche. All right, so there's two things left. The first thing is to go from an array of objects to a single object, and the other thing left is to get rid of this key value grossness. Let's do the key value grossness. It's kind of hard. I think my brain's not big enough to process that immediately. So what's our signature to map? It's a lambda function, right? And what are the args we need? Arguments to our lambda function coming in. It's an object, so let's destructure it. Oops, keep doing that. We're going to need the key and the value this time, right? So we're getting rid of our key value grossness.
So why do you just not call it X? Because then you have to refer to it as X.key.
Right, and that's the main reason in this situation. But in other situations, the main reason to do that is to add clarity to your function. Say, here's what I'm expecting to come in on this object. Super awesome, like self-documenting code. Okay, so how are we going to do that? Let's rebuild our object. So if we're going to return an object, we need to wrap it in parens, I think. And then for our key, we'll use the value of key. And for our value, we'll just use the value of value. Okay, is that going to work? Did I do that right? Good point. Just run it, right? If it blows, it blows. Okay, so we got rid of the key value grossness. Last thing is so somebody said reduce, and that's right, because we want to take an array of n things and we want to end up with one thing. So what was our signature there? They're pretty much all really similar, right? Oh yeah, accumulator and current. And then we're doing a lambda function like always. And we're going to return an object, a single object. So we're going to need to do that little dance again. And then We're going to use object spread. This is a ES next. Is that what we call it? It's not even ES6. It's after that. It's like an array spread. What's that?
Stage 3.
Stage 3. Yeah, as of last week, right? Okay, so we're gonna take whatever we've built up so far and spread it out. So accumulator is what we've built up so far. We'll spread it out into our object, and then we're going to spread out the current one coming in like that, and that's how we'll build up our new object. Ta-da! All right. Oh, still going. Okay, there. There's the answer. We're close. We didn't do exactly what I said, but that works too. And so, in conclusion, what all the things? And that's it. Any questions? Yeah.
It seems like, in terms of, you could have done one for loop and then done all three of those, and it seems like big O complexity would be better with just one for loop, as well as you only have to then deal with one object instead of having to store 3 objects in memory, right? Isn't this more expensive to do it this way? Am I thinking of that wrong?
I don't know if it's more expensive or not, but I think you negate the expensiveness of it by gaining the clarity in reading it. So, like back to our really early examples where we had to parse and analyze the code in our head to figure out, okay, well, I'm looping on this, keep track of that variable, what am I doing here, I'm doing that to it. Whereas you can just say, oh, I'm reducing like this, I'm mapping like this, I'm filtering like this. That's opinion, it's my opinion. Maybe there's cases where it might just be better to loop. But back to performance, I think it's not going to matter until you get such large volumes of data, or you have an extreme case. And I'd say default to the functional paradigm, and if you have a performance problem, address it.
So, this is all new to me. I'm more of a backend guy, but